Now we look at phase and group velocities. Welcome to another lecture video. We're considering phase and group velocities. Now, when we propagate, depending on the wave, if the wave is a superposition of several individual waves, then each individual wave adds its velocity, then the entire group superpositioned, which lead to modulation, will have its own velocity, which is the group velocity. We want to look at the definition, also look at the relationship between the two, particularly as the wave propagates through the medium. Phase velocity is the velocity at which the planes of phase, crest, or thrust of a wave propagates through a medium. If you take a particular wave, the velocity at which such a wave propagates, with one-dimensional, two or three-dimensional wave, the velocity with which this wave, particular wave, propagates is called the phase velocity, and it's also referred to as the wave velocity or wave speed. So what I've been dealing with before now, which we call wave speed or wave velocity, can also be referred to as the phase velocity. Please note that. And also be referred to as the phase velocity, and it is represented as v subscript phase, or see some people write it as v, or you see they write it as v, then now put p subscript, so that's phase velocity. And this expressed as the ratio of the wave frequency to the its wave number. Wave frequency to its wave number. Recall that angular frequency of a wave is 2 pi f, which we said is also 2 pi v over lambda. And you know that k, which is wave number, is 2 pi over lambda. So that means omega, if you do that now, that means omega equals k. What I'm circling here now is k. That's 2 pi over lambda. K then v. So that's where we have this equal to omega over k. Again, omega is the angular frequency and k is the wave number. So for a particular wave, that's the wave velocity or the phase velocity. Now we have group velocity now, and this is the velocity of an envelope of wave, that is two or more waves, two or more individual waves that are modulating or propagating. The velocity of that group, when treated as one, that group of two or more waves treated as one, their velocity is the group velocity, and is represented as, you could say the right is v subscript group or you see it as BG. Okay, yeah, you can see it as is the ratio of the changes in the angular frequency of the individual uh, the individual waves to the wave number of the individual waves. So for example, if you have two waves, so group velocity is just differentiating the phase, the angular frequency of these two waves and dividing by the difference between the wave number. Although it's not usually as straightforward as that, so we see further expression. Okay, so we can say it's the derivative of the angular frequency with respect to the wave number, and at times it may be written as c over n sub g, that is speed of light in vacuum divided by the refractive index of the medium with that group is propagating. Let me just use this image to show you. If you check the left top corner, or sorry, right top corner, you see three different waves. They have different velocity, and they're also actually not really in phase, if I'm right. Okay, maybe the first and the last are in phase, but you will see. Now, these three superposed, then modulation takes place. And the modulation, what we have here, this is modulation. You can see that. So they have the envelope. Let me trace out the group. You see the group. So that's it. Like that. So that red line I trace, the velocity with this such wave is moving is the group velocity, and the velocity will reach the inner one, the changing wave with changing amplitude. The one that I'm tracing, I see the amplitude is changing. It's called the phase velocity. Okay, the phase velocity. So here you can see clearly now the left bottom corner, the group velocity and the phase velocity. We can now derive the relationship between the group velocity and the phase velocity from my initial expression, group velocity, which is d omega dk. So omega is equal to kv. We differentiate straight to k, no special derivative straight to k. So using product rule, you have v plus k dv dk, and for that you can split, and in the final expression you will have v minus lambda dv d lambda. So if you are given the wave velocity of each wave and the wavelength of each wave, then you can obtain the group velocity and obtain the group velocity. So where this is the average velocity of all the individual waves, this is the difference between the velocity, differences in their wavelength, and the average wavelength of the individual waves. So we can obtain the group velocity. Also, we can also express it from there. We can now determine the type of medium through which a wave propagating. If the velocity, wave velocity, and the group velocity are known, can now determine the type of medium such wave is propagating. Can know whether such a medium is dispersive or not dispersive. Now, a passive medium is a medium that splits waves into their different component, group wave into different or individual components. That's what the dispersive medium. So you can know this. For example, when your group velocity is equal to the phase velocity, when you have this condition, after solving, your Vg equals to your V, which means for that to happen, that means your dV d lambda is equal to 0. When that happens, then such a medium is not dispersive. There's no dispersion. There's no dispersion at all. Such a medium is not dispersion. Okay? That is, there is no separation of the wave group into its individual components. And it also means that all components of the waves will travel through the medium at the same velocity, regardless of their frequency. Then the phase velocity does not depend on its frequency. Okay? Then let's see the second case. When the differences that did the change in velocity with wavelength is positive. When it is positive, then it means that the group velocity will be lower than the phase velocity. Okay, and when that happens, then we have what is called normal dispersion. That's normal dispersion, and this normally occur in transparent materials. Normal dispersion normally occurs in transparent material. That's what you have. What happens in your glass prism? That's normal dispersion. When you see rainbow, that's what happens. Normal dispersion. Okay. Then when your dV d lambda is negative, then the group velocity will be greater than the phase velocity, and that rarely occur. Okay. When that occur, you are refer to such dispersion as an anomalous. It's an anomaly. Okay, anomalous dispersion, abnormal dispersion, anomalous dispersion. Okay, and this type of dispersion occurs in medium that has strong absorption bands. Okay, when you have medium with strong absorption bands, then we have such type of dispersion. Okay, so again, dispersion is the separation of wave into different components due to the medium through which wave propagates. For example, you have there is one example that you're very familiar with. Secondary school is your glass prism. White light to glass prism gives you 7 colors. Roy give your red, orange, yellow, green, blue, the go violet, and also the rainbow that you see. Light from the sun is white. It's called white light. When it passes through a evaporable medium, dispersive medium, then you see the dispersion separating into different colors, and this plot shows you the relationship between such in a non-dispersive medium. You see the plot of omega to k, you have a constant slope. That is, there is a constant rate of change of the angular frequency with wave number as wave propagates. When the dispersive medium, it's not so. There is non-linear change in the angular frequency with the wave number. You see. Likewise, in the both any other normal dispersion or abnormal dispersion, that's what you have. So please note this, and if you have questions on every of the video, please you can contact. If you need clarification, I can see put more videos to clarify your questions or respond to your comments under it. Please stay connected and subscribe to this channel, as more videos will be coming very shortly. God bless you. Thank you.